Yo, what is up? Welcome back. This is our second part on a deep dive on linear regression. So we're going to continue where we left off. This time we're getting the gradient descent. What that actually is, we'll get then into doing some partial derivatives, some calculus, some of the nitty gritty, right? So grab yourself a cup of coffee, cup of tea, whatever, beverage of choice, and join in on the fun. Let's get to it. All right, quick refresher on sort of big things of where we left off if you didn't join in the last session. We have this mean square error loss function that tells us how far off our model is. And the way we were talking about reducing this loss was taking this hot, cold guessing game approach where you kind of set up your parameters with just initial random guessing, then compute the loss. Change your parameters, compute the loss, and see if it got better or worse. And if it got worse, go the other direction. If it got better, keep going in that direction. All right. So what we're going to do now is talk about a strategy for changing your guess and making sure we're going in the correct direction. So we don't have to do a hot and cold guessing game. We can just make an iterative approach to getting better at it. All right, so we're going to talk about what gradient descent is. Gradient descent is actually much older than machine learning is, and it's a very common starting point for other machine learning algorithms. So let's go ahead and get into this. General idea is we will calculate the gradient of your loss function at your starting point. And so what is the gradient? The gradient is the vector that points in the direction of the steepest increase. Okay, so a lot of times if you're just doing introductory calculus, you have just a single variable function, you take the derivative, it tells you the rate of change, right? So we're just getting a little bit more general than that. Let's start writing some things down here. It's a vector that points in the direction of the steepest increase. So let's start out with, let's say, idea. The gradient is a vector that points you in the direction of the steepest increase. Points you in the direction of the steepest increase. Just using that kind of loosely, but like steepest increase. So for example, if you have like a three-dimensional hill or something, you know, you can go up the hill in a variety of ways, right? But depending on the shape and the terrain you're on, if you're hiking or something like that, right? You can, you know, at certain points, if I go this direction, the slope isn't as steep, right? But if I go this direction, the slope maybe is steeper. So it gets you up the hill as fast as possible, right? But in terms of loss, we'll calculate the gradient of our loss function, and then we want to go in the opposite direction of that because we want to reduce loss. So the idea is to calculate the gradient and go in a negative direction. So let's go ahead and just get I like to do a little bit of a visual idea. Visually, we can hopefully help make this make some sense. So let me go ahead and let's just put down a little axis here. Oop. Let's try that again. Okay. Perfect. Looks good. Okay, so let's say we will have, let's just to help visualize, the easiest to visualize in 2 dimensions, let's take our loss function on the vertical, and for example, let's say that this is the value of some weight in our linear regression model, value of weight, I'll say W1, right? So we have something like a predictor y is equal to W0 plus W1 x1, so maybe just a simple linear regression model. right? And we're trying to figure out what are the values for W0 and W1 that would give us a line of best fit. So the loss, as you change the values for W1, the loss will change. So I'm just going to make up a random sort of thing here, okay? So let's say this is sort of what our loss function looks like, right? So obviously your goal point is to minimize that loss. So this is going to be the best value for W1. That spot right there, that little blue X, okay? So what happens is when you do this, you have a starting point. So say we just randomly started a value for W1 and we computed the loss, for our starting point, and that put us here. So let's say that this is our starting point. Initial guess, right? We calculate the gradient at this point. Now the gradient is going to point us in the direction of steepest increase. So the gradient is going to tell us to go left, to go for the direction of steepest increase. So we want to go in the negative of that direction. So the negative of that gradient is going to say we have to go this way. So that is the negative of our gradient. Negative of our gradient is there. So what we do is we were going to go in that direction, and then we would repeat. So this is the negative of our gradient. So we're going to go to this to the right and update our coefficient. So now if this was our first choice for W1 was here, now our second choice for W1 is going to be right here, and we're getting closer. So then this is our second guess. And you would do it again, right? And you would go ahead and do it again, right? So gradient descent repeats this process, attempting to converge. Hopefully you converge, and eventually you land at the sort of optimal choice, which ends up being this point right there, okay? So that's what we have for gradient descent. Now, one thing that's kind of interesting about this is note that if we started on the other direction here, or we took a step size that's really large, we might overshoot that minimum value, right? So think about what would happen. Let's say so we have this second point right here. Let's say we took a huge step size. Or step size is how far we're going in that direction. So let's say my step size, let's just say I go there. That's the negative of my gradient, and I go really far. And then I have a third guess point that's over here then, right? So maybe that moves me over here. That brown color is really kind of hard to see. I'll make that big. It's kind of not a great color choice. Third guess. Kind of a goldish color here. Third. Well, let's do something better. Let's use pink, maybe. Maybe that'll calm through a little bit better. Okay. Yeah, that's better. Third guess. If we overshoot it, now the gradient, the vector of the steepest increase, right, is going to tell me to go to the right. So then I'm going to go back this direction, which would be the negative of my gradient. And then so now I have a next guess, which is going to put me over here. So we would converge back and forth as long as our step size isn't too large, right? So there's a lot that we could discuss about this, like this choice of that step size. Generally speaking, small step sizes will help you avoid this idea of overshooting. But a large or a good choice in step size can help you converge and get to that minimum more efficiently. So in terms of talking about that step size that you might be having here, that step size issue, that's something we can address and look at in more detail later on. And there's ideas for, choosing varying step sizes, right, depending on the value of the gradient. If the gradient is extremely steep at certain points, then maybe you don't want to take a large step because it's already going to change a lot. And there's some things like that. We could also talk about the issue where what if we have multiple local minimums as well. And we'll actually get to that once we vectorize our loss function. It turns out that with like the linear regression questions that I'm trying to look at with doing this, we end up having just one it ends up being a convex problem, and so that local minimum thing isn't an issue. Let's come back to all those ideas later. Hopefully we have an idea of what gradient descent is now in terms of helping you get to the minimum without actually just solving for and identifying a minimum, right? In order to get the gradient of our loss function, which is our mean square error, the L2 loss function, let's take a moment to get a refresher on some calculus stuff that we're going to step through. And this is some of the nitty-gritty that is needed to go on to the more advanced problem and what goes on behind the scenes for us, right? So I want to start out with a little bit of a note on partial derivatives. Okay, it turns out the gradient is really just several partial derivatives. So we need to revisit partial derivatives in case we haven't done this in a while. This is the function f of xy of two variables, e to the 2y times sine of x. E to the 2y times sine of x. So we use this notation to take the partial derivative of f with respect to x. So to do so, we just treat x as constant. We would treat y as constant. I misspoke. Partial of f with respect to x. Treat y as constant. So the partial of f with respect to x, if we treat y as a constant, then the e to the 2y term is just a constant that's going to sort of tag along for the ride. So we have e to the 2y. Then we take the derivative of sine of x like you normally would. Derivative of sine is cosine x. And that's the partial derivative of f with respect to x. On the flip side, we can do the partial of f with respect to y. And now we would treat x as the constant here. So the partial of f with respect to y, we take the derivative of e to the 2y just like you would take the derivative of any other exponential function with the chain rule. That's 2e to the 2y. And then if x is constant, sine of x is just some number. And so now that's the constant piece. So that just tags along for the ride with the constant multiple rule. So there are my two partial derivatives. We could do more practice of partials if needed, or if you haven't encountered that yet in your mathematical adventures. What happened to my T in derivatives? Derivatives. There we go. That looks better. So, partial derivatives. Cool. Gradients, then. Gradients. How's that green look? That is okay. I think we can read the green. Let's go. The gradient of a function is the vector of partial derivatives with respect to all of the independent variables. So if we take this, what happened up here? Our function f of xy, which is e to the 2y sine x, and we want the gradient of that. So the notation here is kind of is delta, which is like an upside down triangle. If you delta f of x, y is a vector, so you can do whatever notation you want to contain your vector here. I'm just going to use parentheses. I'm not going to be too picky on that. It always changes depending on the discipline you're in, or whatever types of problems sometimes you're working on. Some people like to use brackets. Some people use the hard angle symbols, that kind of stuff. Anyways, so the first component of this vector is just the partial of f of x. This is as a function, and the partial derivative of f with respect to y. And we want to see that as notation. So in this case, the gradient of f of xy, the first component, is just e to the 2y times cosine of x. And the second component then is 2e to the 2y times sine of x. And there's our bloop. So that's a vector. So this tells you the direction, the greatest direction of increase in the x direction. This tells you the greatest direction of increase in the y direction. So that two-dimensional vector, that gives you the x, y direction you need to go in to increase most efficiently, right? So in our case, we would want to go in the opposite of that direction. In our case, you'd want to go in the opposite of that direction, right? So, for example, let's say I was starting at the point 0, 0. So the gradient here evaluated at 0, 0 at the point 0, 0. Let's see here. E to the 0 is 1 times cosine of 0. That is just a 1, I believe. And then 2e to the 0, that's going to be 2 times 1. And then sine of 0 should be 0. So 2 times 0, so it's just 1, 0. So this is telling me to go 1 unit in the x direction. So my vector points directly horizontally in two-dimensional space. That's the direction of greatest increase. So if I wanted to change and go in the other direction, I would want to go backwards, right? So I would want to go in the opposite. I'd go in the negative of this. So I would go -1 there in that sense, and scaled by some step size, right? Whether it's 0.1 or 0.01 or something like that, right? So this is saying the vector of greatest increase in sort of two-dimensional space, is this vector. So if for some reason this was attached to our loss function, I would want to go the opposite direction and adjust my coefficients that way. And I know I'm getting closer to my minimum because I'm not increasing my loss, I'd be decreasing it. So that's the cool part of that. Are we ready to try to take then the gradient of our loss function here? I think we can do that. How much time do we have right here? We're at 17 minutes. I always like to try to keep these between 20 to 30 minutes. So let's give it a shot. Let's give it a whirl. So, a real hardcore example calculation. Let's consider just the simple linear model. Simple linear model. So y prime is our predicting values. B plus wx with the mean square error loss function. So if we're going to do the mean square error loss function, I'm going to say L is our loss. The mean squared error loss function, 1 over n. Right, we'll take the squared errors. So I'll take my observed value for my yi's. I'll subtract the predicted values. The y prime here is my predicted values for that notation. Square it, that's my error. And I want to sum over all of my data points. So I'll say I goes from 0 to n. So for our loss function, if this is our predictions, then we can put that in for the yi's. So we can write our loss function is 1 over n times the sum as I goes from 0 to n of yi minus, I'll just substitute this in here now. So this is going to be b plus wxi quantity squared. Quantity squared there, right? Yeah, I think that looks good. Okay, so to get the gradient of our loss function, I need the partial derivatives with respect to my independent variables. In that case, I need my partial derivatives with respect to b and w, okay? To get the gradient of L, we need the partial of L with respect to w and the partial of L with respect to b, that bias term, okay? Let's go ahead and take the partial of L with respect to w here. Okay, we're going to write this out. This will get a little bit messy, but we can stick with it. That's the whole point of this thing being a deep dive. So I need the partial derivative with respect to w of my loss function L. So that's the partial derivative with respect to w of 1 over n times the sum as I goes from 0 to n here, my yi's, minus b plus wxi quantity squared. Okay, so we're taking the partial derivative with respect to w, which means, for example, like the b is a constant value, right? So there's a couple of things we can do here. Also, n is constant as well. So let's do this carefully. I'm going to go ahead and take the 1 over n out. That's just a number. That's a constant multiple in my derivative. So I'm going to do 1 over n times the partial with respect to w of the sum. I goes from 0 to n. Now, in order to take this derivative here of w, you have this w is inside something being squared. That loss function there being squared. So I'm going to go ahead and expand this out so that I can take the derivative, right? So these parentheses on the inside don't do much other than just distribute the negative, so we got to make sure we do that. But then we're going to go ahead and just sort of FOIL this out. So I'm going to have my yi squared, right? And then minus 2 times yi. So I'm going to have, right, you've got like a minus b squared is a squared minus 2ab plus b squared. So I'm just doing that where I've got my a's and my b's here. B is a bad choice there as an example, but I think you get the point. So minus 2 times, so I'm going to have yi times b, and then I'm going to have yi times wxi. Wxi. There we go. So that's my middle cross product term, and then plus that second part squared, plus b plus wxi squared there. Okay, there we go. Looks good. I'm going to scroll up here so we can still fit it on the screen. This giant camera in the bottom corner. Could probably make that smaller somehow. We'll see. Where are we now? Let's clean this up a little bit more. 1 over n times the partial with respect to w. And then the sum from I equals 0 to n. And let's clean this up a little bit. So we've got the yi squared. We've got minus 2yib, so distribute that. Minus 2yi wxi. And then I can FOIL this thing out as well. Plus b squared plus 2b wxi plus wx. So it's going to be wxi squared. So let's do w squared xi squared. There we go. And I think that's it. That looks good. Okay. So now I think we're at a point here where we can start to look at actually calculating the derivative here then with respect to w. Let's see. Have I made any silly mistakes yet? I don't think so. I'm trying to be very careful here. No, I don't think so. Okay, so let's go ahead and continue forward with this. Equals 1 over n. Is this line going to get cut off? I think it will. I'll scroll up a little bit more. There we go. 1 over n times the sum. I goes from 0 to n. And now we just go ahead and take our derivatives with respect to w. So the derivative of my yi squared with respect to w, we were treating that as, well, that actually just, that observation there, that is a constant. So the derivative of a constant there is 0. So that looks good. And let's see, what else do we have? Minus 2yib. B is also constant here as well because we're taking the partial with respect to w. So I have minus 0 here. Minus 2yi wxi. Okay, so now we have a term with w. So everything else here is treated as a constant. So we just have a first power of w. So the partial there, the derivative is just 1. So we're going to have our constants carry with us. So minus 2yixi plus b squared. That derivative there is 0. We have another single power of w. So the derivative of that is 2bxi. So there we go. Those are my constants that tag along for the ride. And then we have a w squared xi squared. So the derivative of, well, the xi squared is just like a constant. And the w squared, well, that's just you take the derivative of w squared, use the power rule. So that is 2, bring down the power. So I'm going to have 2w to the first. And then I have xi squared. Xi is constant. Let me write the xi in front so you can try to remember that that is a constant. Xi squared is constant. There we go. That looks good. So let's see what we have here. Let's clean this up a little bit. We'll do a couple things. First is we have some zeros we'll get rid of, but I want to mention that you've got a 2 here, a 2 here, and a 2 here. So I'm going to take that constant factor of 2 out in front equals 2 over n. Summation I goes from 0 to n. Okay. And then let me just go ahead and clean this up a little bit. I'll write my positive terms first. So I have 2xi squared w. No, I don't have 2 anymore. I factored that out. Whoop, factored that already. So this is just xi squared w plus bxi minus yixi. Yeah, there we go. I think that looks good. So we have our partial derivative with respect to w here. Now, if you look it up, you're probably not actually going to see the partial derivative look at like in this shape. So we're going to sort of force some manipulation here. And there is some good reason for this. In the sense that I can also factor an xi within the summation out of each of these terms. So I can do that. So I have 2 over n times the sum as I goes from 0 to n. So within the summation here, I'm going to factor out an xi. And that's going to leave me with what? xi w plus b minus yi. xiw plus b minus yi. And you might not see it yet, or maybe you do. I didn't see it, but if I reverse the order of the subtraction inside of this here, so I'm going to go ahead and factor out a -1 across the board. So this is equal to -2 over n times the sum as I equals 0 to n. Okay. And then I've got my xi. Now, if I factor out a -1 here, I'm going to reverse basically the order of the subtraction. You essentially have this term minus this term. So I factor out -1. So then I have yi minus, I'm going to write that as b plus xi, b plus wxi. There we go. Just taking advantage of some algebraic manipulation. Now, why go through all that? Because now, hopefully we see it. This right here, b plus wxi, that's just the model prediction for I. This is just the model prediction. This is just the model prediction yi prime or yi hat, whatever notation we're using. So this is awesome. This is typically the formula C if you look up the gradient for the mean square error loss function in a simple linear regression problem. It is as follows: negative 2 over n times the sum as I goes from 0 to n, and then we have xi times, times yi minus the observed yi, or not the observed value minus the predicted value difference. Boom. And remember, this whole string of equality, this is the partial derivative. Where do we start? Right. Partial of L with respect to W. This is the partial of L with respect to W. Okay. So that's not so bad, because if you look at calculating this, that's kind of cool, right? So the partial of L with respect to W, in terms of, remember where this started. We started with this derivation. We're looking at the mean square error loss function here, right? Yi minus the predicted value quantity squared. So what you have here is a pretty simple calculation to implement, right? You have your future value, then you have the difference between the observed and predicted value. Add those things together, and this is where the negative 2 over n comes from. The 2 comes from factoring that out. The negative is just there to, in my case, to help recognize that we have the predicted value. You can actually just leave it as positive 2 over n, and then you would just have the predicted value minus the observed value. Notice that you're not squaring this here, so that order and that subtraction does matter, okay? How are we doing on time here? Oh, we're over 30 minutes already. So I think that's enough to sort of see how the gradient calculation works in a simple linear regression on the mean square error loss function. You can repeat this calculation. You should try to do it for B. And you're going to have basically a lot of the same stuff. We didn't even get to taking the derivative until we got to essentially this stage right here is where the derivative actually comes into play. So all the algebra above is fine. Now you could just take the derivative with respect to B and simplify in a similar fashion. So we'll just say in a similar fashion, the partial of L with respect to B is negative 2 over n. And so that negative 2 comes out in the same way it came out over here. But you take the derivative with respect to B. If you just look at the terms you have there, it's just a nice observed value minus the predicted value. There we go. And that is all we would need to calculate the gradient of our loss function, right? The gradient of our loss function. So if we wanted to compute, let's bring this full circle, to compute one full iteration of gradient descent. This one's going longer than I wanted to. I'm getting close to 35 minutes. Let's compute one iteration of gradient descent here, right? So to compute one iteration of gradient descent, we just need to update our values of W and beta based on the value that we have here, okay? To compute one iteration of gradient descent. So let's say we started with just some random initial values, W0 and B1, and suppose we have some step size h. So if our initial guesses were W0 and B0, then I would update them. My next guess for W would be my initial guess minus, and we'll take some step size h, because we talked about that step size at the start. You don't want to overshoot, go back and forth. Some step size h minus h. So that's just going to scale down our partial derivative of our loss function with respect to W, evaluated at the initial point using the values for W0 and B0, right? You have to use those initial values because you have to calculate a predicted value right here in that loss function. So what do you use to predict? You use W0 and B0 to do your model predictions, and we calculate that. And so then this would be our new thing for some arbitrary step size, H. So our next iteration, B1, or our next value for the next iteration for B1, same idea. And we look at the partial with respect to B, evaluated at the initial guess for the parameters. And this is essentially sort of that iterative approach. You could basically sort of say this is, and you just repeat this process, right? You just rinse and repeat there, okay? So that's pretty good. If you were just doing a simple linear regression model, you could already go in. I mean, this is what we need to go in and code up for a simple linear regression model, right? The thing what we want to do here, where things get even more hairy, is this is just for a simple linear regression model where we're doing basically a single, line b plus wxi, right, which looks like y equals mx plus b. But we want to do a more complicated linear regression model where I have more features in it. So the next stage that we want to do here is extend this to multiple linear regression. We want to vectorize these functions and take the gradients there, which is actually where, why we're using gradients instead of, the word derivative, because we're going to have multivariate functions all over the place, right? We will save that for next time. So we'll cut this video here. Hope to see you then.